Okay, so I told you guys that I would go over calorimetry briefly. I'm going to have you calculate one problem and then we're going to move on to chapter 18 because I need to get some stuff done. So we started off with calorimetry. Calorimetry is a nice technique that allows you to measure the amount of heat that's absorbed or released during reactions because it can, you've got, say, this styrofoam cup, which is typically right here, styrofoam cup. And it's insulating so that you're not losing heat to the surroundings and you're just measuring heat that's happening in the system. So if you have what we've been working with is water and then you drop some sample in it and you can measure the difference in temperature and that tells you how much heat is going to be released in the system once you know certain things. So just as a reiteration, enthalpy, we did this in our notes before, but enthalpy is the amount of heat in the system. It's the change of enthalpy. It's the heat absorbed or released at a constant pressure in a system. So enthalpy is the symbol H. It's also heat, which is Q. So just keep in mind that whenever you see delta H or Q, they're the same thing. Heat and change in enthalpy are the same thing. The delta H is the change in enthalpy, which is the heat in the system, and Q is the heat in the system. So it's the same thing. Just keep that in mind. Also keep in mind that if you see a delta H that's negative, that's an exothermic reaction, and a delta H that's positive, that's an endothermic reaction. We talked about that before. But let's get into some of the practice problems. I like this one. You have a copper coin, and it's heated and placed in a foam cup calorimeter, which is what you were doing before. And it contains 32 milliliters of water at 22 degrees Celsius, and the water changes to 24 degrees Celsius. How much heat was released by the coin? First of all, the fact that it's been released is telling you that it's an exothermic reaction, so you should have a negative answer. But let's calculate this. So what do you know? You know that you have, so your knowns, you have 32 milliliters of water. Problem is we need mass of water, and I've given it to you in milliliters. It's an easy switch because water just so happens to have a density of 1 gram per milliliter, which makes this into 32 grams because it's for every 1 milliliter you have 1 gram. If you have 32 milliliters, you have 32 grams. So I have 32 grams of water. My change in temperature, you subtract the first temperature from the second temperature, and I wind up with 2. My specific heat of water, because that's what you're dropping this thing into, dropping this copper into, is 4.18. So then just use the formula that we've been working with, and you get Q, or delta H, equals mc delta T, and you plug it in. And because it's being released, you should have a negative. So my mass is now 32, negative 32 I should say. My C is 4.18 because that's the specific heat of water that's on your reference sheet. And the change in temperature is 2 degrees Celsius. When you multiply all those together, you wind up with 268 joules. Fairly easy. But let's do another one. Now I've got a 2.5 gram sample of zinc that's heated, and you pop that sucker in a calorimeter containing 65 grams of water. The temperature increased from 20 to 22.5 degrees Celsius, and it gives you the specific heat of zinc, how much heat is released by the metal. Here's kind of the trick. If they're asking you, if they're giving you a lot of information about the zinc, make sure that you're using all the information on the metal and you're not worrying about the water. So I'm going to ignore the water. I'm going to be focusing on the zinc because I have enough information to be able to calculate how much heat is being released by the metal. I've given it all to you. So here's how you would do it. So what do I know? No. I have my mass is 2.5 grams of my metal. The specific heat of the metal I gave you and that's 0.390. And the change in temperature, when I subtract those two temperatures, I wind up with 2.5 degrees Celsius. When you multiply all those together, it's 2.5 times 0.390. My goodness, not sure why my stylus is not working. And 2.5. And you wind up with 2.43 joules of heat released. One last one, and then I want you to calculate the final one in your notes. So this one's a little bit more complicated, rather it looks like it's a little more complicated. I have 25 milliliters of water, and it has dissolved into it 0.025 moles of hydrochloric acid. And the temperature is 25 degrees Celsius. And then you add that to another 25 milliliters of water containing 0.025 moles of sodium hydroxide at the same temperature, 25 degrees Celsius, in a foam cup. You get a reaction. And I want you to calculate the enthalpy change in kilojoules during the reaction if your final temperature is 32 degrees Celsius. I also tell you that assume the densities of solution for every 1 gram, water is 1 gram per milliliter, and the volume of the final solution is equal to the sum of the volumes of the reacting solutions. Sounds overly complicated. It's not at all. You have to eliminate most of that stuff. I've given you a lot of extraneous information. Of which is, let's look at our knowns. What do I know? I know the specific heat of water, 4.18. I know my volume that I'm going to be looking at. I'm going to add those two volumes together of water. The first volume of water is 25 milliliters. Second volume of water is 25 milliliters. So I have a total of 50 milliliters of water. Remember, for every milliliter I have a gram, which tells you how many grams of water I have, right? I have 50 grams of water. So now it tells you that my mass, instead of 50 milliliters, I have 50 grams of water. My initial temperature was 25, my final temperature was 32, so that is a change of temperature of 7 degrees Celsius. So then I just plug that sucker in, and it's releasing heat, so that's a negative delta H. So delta H, which is the same thing as Q, is negative MC delta T. So I wind up with, my mass is negative 50 grams, specific heat of water is 4.18, and the change in temperature is 7. So I wind up with negative 1,500 joules, but to add a little bit extra layer, I want my answer in kilojoules. Whenever it's a kilo, you divide it by 1,000, and I get negative 1.5 joules is my answer. Not hard, just got to realize what you're plugging in. Last one is what you're going to do, and it's right here. I've got a small pebble that's heated and placed in a foam cup calorimeter containing 25 milliliters of water at 25 degrees Celsius. The water goes up to 26.4 degrees Celsius. How many joules of heat are released by the pebble? You don't need to know the grams of the pebble at all, because I give you milliliters of water. So you know then you have 25 grams of water. You know the change in temperature, and you know the specific heat of water. So this one's actually fairly straightforward. Make sure you're putting this in your notes. And that's it.